So today's subject is, I'm telling it, how did we get here? But what I'm really focusing on in the first half of the talk is the latest results from the James Webb Space Telescope. And as you'll probably see, this is very much a thing in progress. We're seeing a lot of things, but we're not yet having a coherent picture of the whole thing. We're still in the stage of seeing things, and then the next step is to try to put them all together and understand it. So here's, why does it do this? Now, I've shown this graph several times just to summarize the history of the universe. Well, maybe not everybody has seen it, but so we had some beginning here, and then there was the period of very rapid inflation of the universe. Then about 380,000 years, the universe became transparent, and we still see the black body radiation from here. And then after that, there was a period of not too long, a couple 100 million years. Well, by our standards, it's kind of long, but and then the first stars began to form. And then after the first stars formed, the universe has continued to evolve, and things have changed. But basically, that's the period. And the Hubble Space Telescope could reach back to something like 500 million years after the start, after the Big Bang start. But the JWST, yes?
You've gotten out of screen share.
I've gotten out of screen share.
It says it's screen share.
How do I get back in? Am I out of everything?
I see your screen loud and clear.
Why?
And I'm just,
I do too. It's fine.
I think it's fine. It's fine. It's fine. Thank you, Benita.
Is it fine?
Yes, it's fine.
Fine, fine.
Okay, all right.
It's fine.
Thank you. It's fine.
The JWST, this instrument, was designed to investigate this first epoch of star formation. The first stars in the universe, the first galaxies in the universe to form. That's what its primary mission was. It had many things it can do, but that was the primary mission. And recall, also I've shown this before, but I find a good way to think of the evolution of the universe is through its temperature. We started extremely high temperatures, like billions of degrees. But in the first 3 minutes of the universe, we formed helium and a few other things, trace elements. And then there's the cooling down to the point where electrons and protons combine and the universe becomes transparent. And then at 200 million years, we get the first stars to form, and then today is here. See, I mean, there's no way to put the whole universe in one graph without compressing the scale somewhat, and this is a very compressed scale, which emphasizes the first instances. But that makes sense because, you know, temperatures are ratios. So new physical phenomena happen roughly at ratios of temperatures. So that the difference between 1 degree and 100 degrees physically is kind of similar to the difference between 100th of a degree and 1 degree. Even though to us it's not much difference, but in terms of physical processes, that's the critical thing. Okay, now I'm going to talk about how stars form, the first stars form, but we've got to get some picture on how stars form at all. And the stars are still forming today. Stars and planets are still forming today. And so that gives us a good insight in how the first stars must have formed. And stars, well, stars have to form out of something. And this is an example those somethings. There's huge, very thick, close star field, but then there's this cloud. And this is a cloud of gas primarily and of what we call dust, smaller conglomerated atoms. And they form these cloud-like things, these dark nebulae or clouds. And it's out of these, because stars have to form out of something, it's out of these that stars form. And it's in these regions that new stars are forming. So here's another example. This is a particularly dense cloud. So it's not the absence of stars here. It's that there's this dark cloud in front of these stars. That's what we're seeing here. A dense material. Yes, yeah, these are actual photographs. And here's some more complicated. I can never look at this without thinking of Walter Adams' comment, this nebula has made an S of itself. And you can actually see these clouds with the naked eye. When you look at the Milky Way in a dark summer sky, you'll see regions, particularly in Cygnus. Well, this isn't Cygnus, but anyway, that's where it's very apparent, where the Milky Way gets very broken up. And again, it's not the absence of stars there. It's that these clouds are in front of the stars, and you're not seeing them. So you can see the clouds with the naked eye. This region here is actually near Sagittarius, and the galactic center is somewhere here. But even though that's a very bright region and very dense of stars, we don't see it because of these clouds. They shade everything. All right, so that's the clouds. Now, so what happens? The basic thing is to seeing the titles here. Oh, well. Ah, great. So the key is gravity. All matter in the universe is attracting all other matter. It's just a basic thing. And what happens in a dark cloud, like this what's called a globule here that I showed before, is that the matter in the cloud, all the matter in the cloud is attracting all the other matter in the cloud. So it's a little more complicated than the solar system, where the sun dominates and attracts the planets. But the planets do attract each other too. I mean, we see effects on the Earth's orbit from Jupiter, for example. Those are measurable effects. And so in a cloud like this, all the matter is attracting all the other matter. So why doesn't it just fall together? Well, the cloud also has gas pressure in it. The gas in the cloud has a temperature, and that exerts an outward pressure. And so in a normal cloud, and these tend to kind of balance. Okay, there's you want to sing there or no? Okay, and so the pressure outward balances the gravitational force inward. But you can get a situation where the pressure isn't enough to balance it. That can happen, for example, when two clouds crash into each other. That can upset that pressure balance. And then the cloud can collapse due to gravity. And that triggers a star. See, all the matter goes down. So, well, here's an example of a star-forming region, and you can see these globules here around the edges, and there has been star formation here. That's what's illuminating these clouds, bright young stars. But you can also see more of these dark clouds, and that's at least possibly regions of potential star formation. So here's what happens. You start with a cloud, and the gravitational force pushes it all together. And this happens very quickly. It's a they're kind of falling in on each other. So 10 to the 4th years, 10,000 years, small on an astronomical scale. And then it collapses and forms the first star. But not quite all the material gets into the star. And some is left over. And that's shown in that disk there. And it circles the incipient star, and that's where the planets are going to be made. And then after only 1 million or 10 million years, you get the planet formation. We see the planet formation and the star in the center, and then eventually all that material is swept out, and we get a solar system. So that's the process of star formation. And we see this here. This is T Tauri. This is a young star that's just a few million years old, and it's formed out of this cloud. And the planet formation effect is also very rapid, because what happens when a planet starts forming, as the planet gets bigger, its attraction gets bigger because it's more massive, and therefore the gravitational force gets bigger. And in addition to that, as the planet gets bigger, it intercepts more material. So the planet formation is also quite rapid effect. These build up, and it's called the Matthew effect for a reason, because there's a thing in the Bible which says, "For whosoever hath, to him shall be given, and he shall have more in abundance. But whoever hath not, from him shall be taken away even that which he hath." I don't know what the point of that.
Amen.
I don't know. I guess maybe Jesus said that. I don't know what point he was trying to make. I need to look
Is
that
there a
up.
reason why in our solar system, the first four planets are basically hard matter and the outer planets are much larger gas giants?
Right.
Is there a reason for that? And is that something that was constant in other stars?
Yeah. Did everybody hear that question?
Yeah.
Well, that's a very interesting question. And before we found other planets in other solar systems, we did have good theories about that. I wrote something about it. Yes, the reason was that inside where it was higher temperature, we could get condensation of things like carbon, silicon, oxygen, and so forth. And further out, it was cooler, and we could get planets could be cooler, and they could hold on to hydrogen and helium and so forth. And that all was a nice theory. And then the first extrasolar system we found outside of our, planets around another star had a giant planet real close to its sun, just opposite of what we see. So they're very complicated. And one of the things that, it's a complicated business, but one of the things we did learn is that planets migrate. And the solar system is somewhat unusual in that its planets aren't moving in and out. But a lot of planets, there's evidence in solar systems that the planets move, that it's a pretty unstable system. Okay, and here's a case of some of these disks that we say found. Here's some young stars in Orion, and you can see disks. All of these have a disk around them, and there's one that's really obscuring things. There's an illuminated disk, and so we see that early disk process. And here's another complicated one, which has a disk with an empty space in between. This black space is a mask over the star, so that we can see the stuff around it. That's not anything real. So it's a mask over the star. But then we see this disk, and this is one where there seems to be a planet, a very large planet, or an incipient planet. That little thing there, pointed to 2012, and it's moving. It's very difficult to see these things, though, very challenging. Okay, so let me get back to the case of the first stars, the first planets. So what's JWST seeing? Well, what we expect to see is that in these, again, this is a theoretical thing, is to see that probably things started with small clouds, and those clouds formed small galaxies and stars at the same time, maybe. And eventually the more galaxies got together and formed clusters, which you can see here. So that's 3. And now a critical thing to all of this, in fact, we didn't really understand how the first stars and galaxies could form at all until we had dark matter. Because the because if there's only matter in the universe, only the visible matter, there was not enough gravitational attraction to form the galaxies fast enough before the universe expanded so much that they couldn't form. But with dark matter, that problem was solved. And with dark matter, the first galaxies can form. There's enough matter and it's dense enough so that stuff can form. That was actually something that was worked out here at UCSC. And the dark matter tends to dominate all this. We don't see it. We talk about the visible matter, but remember there's about 6 times as much dark matter as visible matter. And so here is one of the things that that JWST is seeing. It sees these small little red objects, and which are, this one is 13.5 billion light years away. Z equals 14 is the redshift. And so this is one of the very first things we're seeing. So we're looking at something that the universe is 13.8 billion years old. We're seeing something that's 300 million years. And it's already formed this incipient galaxy. The size is pretty small, 1,600 light years across. Remember, our galaxy is 100,000 light years across. But it's quite massive. It's has something like 100 million solar masses, 100 million suns. So this is one of the surveys. And so if we looked at that compared to a galaxy that we're used to, that galaxy is small in size. So and we're seeing lots of these small things. So the way things are going is going from small to large. The first things are small in size, but again, this mass is 100 million solar masses, so the density is quite high, higher than the density in our galaxy. But that's what we're finding. And now we're finding lots of these objects. That's the first objects in the universe. They've been called the little red dots. Because I don't know, that name will stick, but and this is one of the surprising things that JWST has found. We're finding lots of these earlier than we thought. Some of these are going, we're seeing back to 300 million years, even a little bit earlier. They must have formed even earlier than that. And that is surprising. Our theoretical pictures didn't have galaxies forming that quickly. And they're, so typically they're few thousand light years across. They're red, they're small, and there's many of them. So that's the thing that now we're having to explain as the first galaxies. Now, these are not as photogenic as the galaxies I like to show, or the nebulae, but remember that at the limit of what we can do, it's always going to be fuzzy little patches that we can barely make out, right? That was true for Hubble, and it's true for us today. So these are not going to be as pretty as the other things, but that's where the fundamental science is. You had a question?
Yeah, where you said a little red, does that mean
Yeah.
red shifted or what?
No, they are intrinsically red, and that's one of the questions. Why is that? And there could be 2 possible reasons. One is that there's a lot of dust in it, that dust that I showed in the before, and that is true. There does appear to be a lot of dust, and that tends to make things reddish, just like the sunset is reddish. And the other possibility is, and there's good evidence for this now, is that these have massive black holes in them already in the centers, and that there's a lot of illumination. And the reason they're so luminous is that the black hole is luminous, just like the black hole in a quasar is very luminous. So that's still something that is it one or the other, or is it a sum of both, or what's going on? And so getting straight what's going on in these black holes, stars, dust, we still have to straighten all that out, how that's all working. Okay, you had a question?
I was going to ask if you were actually red. So
They are red.
So Roger, but what we're seeing is what they were like 13 billion years ago,
Yeah,
right?
yeah.
Right.
That's probably what our galaxy was like 13.8 billion years ago, right?
Yeah.
And, but the another question is, they're really small, but galaxies today are big. So there has to be a real evolution of these things coming together.
Roger, how do
One
you
more question.
know how many stars are in a thing that's 13.5 billion years or light years away?
Well, that's tricky. One of the things is you can just ask what is the average luminosity of a star? Actually, the sun is average. There's much more bright ones and much fainter ones, but the sun is kind of in the middle. So you can get a rough estimate from that.
Okay.
What screws it up, of course, is if there's a big black hole, big luminous thing in the center, then that adds to it, and that messes up our estimates. So people are still working on all that. That still has to be really straightened out.
Okay, thanks.
Okay, the other thing that we're learning from this is very interesting, I think, is that these early galaxies, well, here's one of these red ones. This one is not quite as old, 13.1 billion years old. And look at its spectrum. It has oxygen and neon in it, as well as other things. So there has, but we know now the hydrogen and the helium in it, that's not a problem. We know the universe started with hydrogen and made helium early on. But neon and oxygen were made in stars. And we're already seeing it in the gas. So there's already been an evolution of element formation in these things, even a few 100 million years afterwards. So probably very early stars evolved very quickly, made a lot of this, had these heavy elements. I mean, everything other than helium we call heavy, like neon and oxygen, spewed it into the interstellar matter in these galaxies, and we're seeing them. So there's already a lot that's happened. And here's an idea. I realize I'm throwing a lot at you, but there it is. Okay. Here's some comparing some stars. Here's the sun. And it's sort of an average sized star. Here's Aldebaran, probably a familiar star in Taurus that you know about, a lot bigger star. But the first generation we think is even bigger yet. It's this.
Wow.
These are really big stars. And that kind of a star, but we have not yet proved that. That's how we think the first stars are going. And one of the missions for JWST and any future big telescopes and so on is, can we see these first generation stars and can we understand them? But that's this. So this is not yet observed, but that's what we think happens. And in that kind of a star, there would be very rapid evolution. Mm-hmm.
So are we still sticking to the birth of the universe being 14 billion years?
Yeah, 13.8.
Even though this indicates that maybe something happened before?
It's not indicating that. It just, so far to us, it's indicating that things happen very rapidly. Yeah. Good question. Okay, here's some more of these red dots, and so you can see what it explains. See, some of these have really bright centers. It makes you really think. And the black hole evidence, by the way, is getting pretty strong. That probably massive dark matter halos which form black holes very early on. That's part of the formation. Okay, so where are we now? So we've found galaxies when the universe was 300 million years old. We've never seen anything like this before. So this is all new. They make massive stars faster than we thought. There's evidence now, which seems, I think, getting stronger, that there are supermassive black holes. That is, black holes on the order of millions of solar masses. Okay. Now, our own galaxy has a 4 million solar mass black hole in its center. So, right, 4 million suns mass worth. So it's easier to talk in terms of star masses rather than grams, where there's some 10 to the 27. Okay. Now, so 10 to the 100 solar mass, 4 million solar masses, 10 million solar masses is a supermassive black hole, but it's not the most massive we've seen. The M87 black hole has 4 billion solar masses, and there's more massive ones than that. So anyway, but that's what supermassive is. And the elements in the early universe, there's evidence for carbon, silicon, oxygen, stuff like that. And these elements seem to have formed really fast. Okay, so that's kind of where things are right now. There are papers every 2 weeks in the Astrophysical Journal, and but we're still. I think it's probably fair to say, you know, you first have to look to see what's there, and then you have to work to understand it, right? I mean, when Columbus first discovered America, and the news got back, the first thing was just what's there. What are there islands? Are there continents? Is it India? Or who are the people there and stuff like that? And then in the years afterwards, that began to be put together and understood. And I think that's where we are right now with the early universe. We're still trying to get what is there? What are we trying to understand? Okay, well, now switching to something else. In the second lecture, I think I talked about the Hubble tension in that, and this is different, but I'm going to talk about this. The Hubble tension is that the Hubble constant, which is fundamental how the universe is expanding, we get two different ways to numbers for it, for the same thing. And one is when we measure it, that's the, you know, we got, which I talked at some length about how we get that. And that gives us one value, that's late. And there's another way to get it, though, is from our theories of the early universe, how it expanded. Because if it had expanded too fast or too slow, we would have different composition of elements, for example, different amounts of helium. So that's a way to measure the Hubble constant. And the two don't agree. And it was hoped that JWST would help them to agree, and it didn't. We are still having two, so this is a little bit complicated if you don't get it, it's okay. But there are two different ways to measure it. The simple, straightforward, now the late measurement gets us numbers around 73 in some astronomical unit. Yeah, I'm going to explain that. What this means is that this is the Hubble constant, and it means it's expanding at 74 kilometers per second per 3 million light years. So for every 3 million light years, it goes at 74 kilometers per second faster. And that's about 3,600, 36,000, about 210,000 kilometers per hour faster for every 3 million light years. And anyway, the other value is here, 67, and the lines indicate the uncertainties that we think we have. And it's not resolved. So it's a very interesting problem. They don't agree, and everybody thinks they're measuring it right, and they still disagree. So that's the tension. And we don't have an answer to that yet. We need to work this out, though. It could be, it's, you know, the obvious thing is always, did somebody just get the measurements wrong or get something wrong? With JWST, they have remeasured this thing, and they got it, and it came out exactly the same as what we got with Hubble. So that isn't the answer. Maybe there's new science going on here. Maybe there's something about our science that we're not understanding. So
constant isn't necessarily constant.
no, it's not constant, but it's the constant. That's true. The Hubble constant isn't constant, but we know what it is today, and that's what we're comparing. So, okay, well, I just thought this is John Mather, who's leading the JWST project, and I thought it'd just be interesting to hear what he has to say about it. Well, that's hard to hear.
It's also, John, turn the speaker. Turn your speaker on your Mac.
Yeah, how do I do that? If this in here, yeah, here we go. Yeah, I'm getting it. It is on. No, that's okay.
What turns me on, what makes me most excited about James Webb, I would have to say it's what James Webb will enable us to discover. We don't know yet. We don't really know whether there's life elsewhere in the universe. But James Webb, in its infancy, has already given us a glimpse of what is possible. Where did we come from? Are there other forms of life in the universe?
Ever since I was a small child, I wanted to know, where did we come from? And so do so many of us. Well, there are lots of ways you can answer this question, but astronomers have the chance to look back in time to see what this universe was like when it was young. We know how fast light travels, so we know how far back in time we're looking when we look far away. So we knew with a telescope, we would be able to see back to when the very first galaxies were being born after the Big Bang. When we started designing the Webb telescope, we knew what the great challenges of observational astronomy were, and we knew where we didn't know. We don't know much about the early universe. We've never seen any of it before. We don't know how stars are born inside their little cocoons of dust. We don't know about the planets. We've only recently found out that they exist. There could be surprises coming to us in all of these areas, but the one that we already know about is that the first galaxies grew differently from what we expected. They seem to be brighter, hotter, bigger, more massive than anyone had expected based on observations with the Hubble telescope and other telescopes on the ground.
So it's a very exciting time from a science standpoint at this point. You know, back prior to launch, the excitement was really on the engineering side. Now we've shifted over to all the excitement on the science side. I mean, Webb is phenomenal. And what I've seen to date, I can never pick out. Okay, I can pick out some favorite images.
The iconic image that I like from the Webb telescope is the first one that we released. President Biden put it out on July 11th last year. It shows a star, it shows a big fat galaxy in the middle, and it shows lots of strange looking curved arcs, which turn out to be gravitationally lensed and magnified images of much more distant galaxies. So this shows the power and potential of the Webb. There are just galaxies all over this picture. So we knew we had the powerful observatory that we wanted and that there would be surprises in it.
Yeah,
We talked about space-time here, the difference of space-time between the two theories, the 9%.
no, the 9% is a difference in the Hubble constant that the two methods measure. The one, which was called late, is a direct measurement. That is, we look at how use Cepheid variables as signposts, supernovae as signposts of the universe, and then from that determine how fast the universe is expanding. The other method, called the early method, is our theory of the universe and how the Hubble constant has changed and how things in the universe have changed, but that has to agree with what we see, like the abundance of helium in the universe. So that's a more theoretical way of going at it. And that, but it should give the same answer. And there we are finding a discrepancy of that 9%.
You know, I remember reading a long ago that Einstein working on the unified theory, and he thought that space-time and bending space-time equals matter.
Yeah.
And but then he died. And what's that? Yeah.
Well,
Explored does it.
I think you're combining two things, actually. The fact that space-time changes shape in the presence of matter, its curve, that's confirmed, that's true. And we see that, for example, in the way light bends, these arcs that Mather referred to. That is bending of light by massive objects, when the light goes near a massive object. So that works. What Einstein spent the last half of his life on was an attempt to create a new theory which combined electricity and gravity, and that was a failure. He never was able to get anything
And
right.
it's still a failure today.
Yes, it's still a failure today. We have a theory which combines the three forces, namely the strong force in the nucleus, the weak force in the nucleus, and the electromagnetic force, which we're familiar with as electricity. And those two combine in a sensible theory, but gravity doesn't fit into that. And that's where there's still an unknown. And a lot of people thought that Einstein's project of combining electricity and gravity couldn't work, even when he was alive, because they said, well, you're leaving out two of the forces. Does it make sense to have a big theory of just two of them and leaving out the other two major ones? But he didn't go with that. Anyway, all right. Here's another thing. I realize I'm throwing a lot of stuff at you, but this one is just sort of for fun. Remember, I showed this on the second time we're here, second lecture, And this is the distribution of galaxies in the universe. Each blue dot represents one galaxy. Okay, so we've mapped the universe, and each blue dot on this graph represents one galaxy. And but it's not a complete thing. The two cutouts here, it's not round because we can't observe in this region because the Milky Way is basically in the way. So there are galaxies here, they're just not done. And we're observing from here, and we're looking out something like 2 billion light years. So not to the beginning of the universe, but 2 billion light years. So this is the distribution of galaxies. And it's also a kind of a pie cut. It's not a three-dimensional thing. But what you can see here is this structure. This isn't what would happen if you spilled peas on the floor, right? There is a lot of structure here. They line up, they form this complicated structure. That's something we need to understand. And here's sort of a three-dimensional attempt to what that would look like in 3 dimensions. The galaxies are formed along these filaments, these lines, with empty spaces in between. To me, it's like, this is not an analogy, but, well, it's an analogy, but it's not a very close one. Like a soap bubble film, right? You have a lot of stuff, and then there's empty spaces in between. And that's because of the two forces that are going on in a soap bubble film. One is the surface tension that you know, like in a soap bubble, the surface tension tends to squeeze things together. The other is the pressure in those open spaces, which hold things apart. And then those working together form these bubble things. That is, the surface tension of the soap tries to pull it together, but there's pressure in here that tries to hold it up. Now, in the universe, we don't have surface tension or that kind of pressure, but we do have that gravity is pulling things together, and the expansion of the universe is pushing them apart. And so that combination seems to give us the kind of structure that we see of these galaxies along line. This is a mathematical description of this. Is this okay? Here's how how the universe might have evolved. This is a mathematical computer description of it. The age is up on top. Okay, so let me show that again, because so at the early part, when the universe began, we think it was pretty smooth. Then with the formation with the action of gravity and of the expansion of the universe, we form these. Okay, that might have screwed everything up again. Where are we? What's going on? So get rid of that.
Can you go down to the zoom thing on your little tray there at the bottom and click zoom on the tray?
On the tray.
Of your screen. Yeah, that, what does that do?
No, I don't think I wanted to do that, actually. Just a minute, just give me a second here.
Oh, you're still in Zoom,
Yeah, I think I'm okay.
Go back to play.
but you're out of the screen share.
Well, let me first try to get the thing back up again here. Am I back in?
Yeah, beautiful.
All right. So, where am I here? It stopped at 7.4 billion. Yeah. Let me go back. Wait a minute, I wanted to show this. All right, here is a smooth universe, and now it's beginning to form these filaments. So that's a subject of trying to that is telling us how the universe is evolving, and it's a subject of a lot of research, and we big telescopes and are going to probably tell us more about how this all evolved.
A question on that. So what we're seeing is the visible mass, right?
Yes. And we think and the dark matter is associated with that, we're pretty sure.
They would be
Okay.
sort of the same picture.
Right, yeah, because although visible mass and dark mass are very different, they are united by gravity. Both of them are pulled on by gravity. Okay, let's take a break.
Oh, my goodness.
Yeah.
Yes.
Yes.
They're just wonderful.
Well, I kind of imitate other drawers.
Wonderful. I love the little shoelace.
I'm glad you noticed that. I thought that was funny, actually. All right. Okay, so I'm going to talk a little bit about the future, where we're going from here. And not so much scientifically, but just what we're doing, kind of stuff we're building. You've probably heard about the 30-meter telescope, big project to build a telescope with a mirror 30 meters in diameter. Which is the biggest one we have right now is 12 meters, something like that.
The mirror, they did one of the mirrors at UCSC, didn't they?
They're working on this technology, but as far as I know, they're not building mirrors at UCSC. Okay, this is a big combination project of Caltech, University of California, India, Japan, Canada, National Science Foundation, and the Gordon Moore Foundation. But this has been in planning for something like 20 years, and we don't yet have a start building this. And to give you some idea of telescopes, this is kind of a complicated graph, but I'll just show a few things. This is the size of the Palomar 200-inch telescope, which was the biggest telescope in the world when we were children. This is the size of the JWST down here, talking about. This is the projected size of the 30-meter telescope. So you see, and as you compare these, remember, and I think this diagram shows it well, we talk about the diameter of the telescope, but what's really important is its area, square of that, okay? And that shows it here. Now, here is the extremely large telescope that the European Southern Observatory is building, which is 39 meters. And so that's the future. I could mention something there. They started by building 4 10-meter telescopes, 10 meters, 8 meters, I can't remember. And they called it the Very Large Telescope. And these were combined, so these 4 telescopes could work together like one. But they didn't have a whole lot of nomenclature. So the next one they called the Extremely Large Telescope. And then they had this whole big gray background was a proposed large, and they called it the Overwhelmingly Large Telescope. But they didn't go along with, that's canceled, that project. It was thought that was going too far right now. And so I don't know if they go even bigger than that, what they'll call the horrendously, impossibly big telescope or something. But here's the deal. The TMT, the 30-meter telescope, was to go on Mauna Kea in Hawaii. And Hawaii is probably the best site on the planet for astronomy. So if you're going to build a really big, expensive telescope, you want to build it at the best sites you can. But one thing that has held it up is that there is a huge movement against it in Hawaii by native Hawaiians and a lot of people who aren't native Hawaiians, but like to pretend they are. And they have successfully held this up for more than 10 years because they claim this is a religious site. It was a religious site for the ancient Hawaiians. And while one can sympathize with the Hawaiians have really been treated badly by the Americans. We all have to admit that. And while you can certainly sympathize with their wanting to assert their identity, unfortunately, it has been to get this site back. Now, one of the things, so it is a wonderful site. This is the Canada-France-Hawaii telescope. This is the NASA telescope. This is the Keck Observatory, which UCSC is involved in. This is the Japanese National Observatory. This is a submillimeter telescope. This is a Gemini, which is a National Science Foundation. These are Hawaii telescopes. This, the highest point on the mountain, this cinder cone here, it's a volcano, by the way, will not be built on. That's going to be protected as the highest site. This is an extinct volcano, we think. The last eruptions occurred not on the summit, but at the base, I think something like 4,000 or 5,000 years ago. This volcano is Mauna Loa, which is a very active volcano. And it last erupted in the 1980s. So it'd be embarrassing if this went off again. Now, here is the European Southern 39 millimeter extremely large telescope. And this is what it will look like. Look at the cars here. It's really big. Okay. Well, 39 meters, you know, a meter is close to a yard. So it's like the 40-yard line in a football field. I mean, it's really, really big. And here it is where we are now. This thing is built. It's there. It's starting to look like a telescope. The first light will be in 2028. So it's on Cerro Amazonas in Chile. Chile is probably the equivalently good or almost as good site as Hawaii. Very dry northern part of Chile. And it's on a mountain of almost 10,000 feet. I think actually this mountain was 10,000 feet until they leveled the top. 50 feet. So, but anyway, Chile is sort of California upside down because it's in the southern hemisphere. And so, whereas in our state, the southern part is dry and the northern part is wet. In Chile, it's the other way around. The southern part is wet and the northern part, the Antofagasta Desert, is dry. And that's where this telescope is being mounted. So they are really ahead of us. No question about that. They're going to get an operational telescope before we've probably even broken ground for the 30 meter.
Is that these are all terrestrial based?
Yes.
telescopes,
Yeah.
right?
Yeah.
And isn't there, I seem to remember, maybe I'm wrong, but that there's a big problem with terrestrial based telescopes because of the distortion, the movement of the air and the atmosphere and distorts the light.
Yeah, that's a good point, but it was. It's true that the earthbound, first of all, one advantage of an earthbound telescope is you can make it a lot bigger than you can with a space-based telescope. So you can actually do better from the ground for certain kinds of observation because you get that huge light gathering power. And remember the 6 meter JWST had to be folded up. It's as big as we can get. We can't put a 30 meter telescope into space. We don't have that technology. Yeah. But what happened is that there are two problems with ground-based. One is that there are large regions of the spectrum where you can't see through the atmosphere. The atmosphere has lots of water in it that absorbs light, and you can only observe where light doesn't absorb, like in the visible region, or the near infrared, or parts of the infrared. So that's one problem. Don't have that problem in space. The second problem was that the twinkling of the stars is caused by the motion of the Earth's atmosphere. And while the twinkling may be romantic, and I have romantic memories of that, it's bad for astronomy because it distorts the image. But we have learned how to solve that. We measure the twinkling, we distort the mirrors, and get rid of the twinkling. Okay, that was a technology. It's actually an interesting thing where astronomy interacted with other things. This idea was first proposed, as far as I'm aware, by Menzel in something like 1952, that it might be possible to have a telescope which measures the twinkling, how the things are, and then corrects for it. But the technology wasn't available until the 1980s. And then the astronomers began to think about, let's try to see if we can build a telescope that would take this technology. We found out that the NSA, the National Security Administration, had just built a telescope that would do that. It was in space, but it looked through the atmosphere at the ground and corrected. And they used apparently Menzel's idea. Well, I don't know what they used because it's all secret and stuff like that. But anyway, it turned out it was there, and astronomers continued to develop this technology. And today we have it. We can correct the atmospheric fluctuations, and those hundreds of mirrors in the ELT are constantly moving to correct for the Earth's atmosphere motion. So we will get really good images. Okay, so that's a long answer to a question. I'll just mention a couple other things we're doing. In 2 years from now, we'll launch the Nancy Roman telescope, and this will be a telescope. It's actually the same size as the Hubble, so it's a very big deal. But it only works in the from the visible region of the spectrum to the near infrared, and it does. And what's different from the Hubble gets very detailed views of a small thing. This telescope will see a huge thing, huge area. It's a very fast telescope, and we will look at millions of galaxies with that, and so we will revise those galaxy distributions that we saw. And we'll see how galaxies were distributed now and in the past. So it's a tremendous result, a tremendous instrument. Nancy Roman worked diligently to make the Hubble Space Telescope work. So she was a NASA administrator, and she's being memorialized by this instrument. So that's really exciting. Now, another project, and this is very far in the future, is the Habitable Worlds Observatory. And its mission will be exactly this. It will be primarily built in order to look at distant planets and look at Earth-like planets and try to see, is there evidence of life, some kind of life, intelligent life, bacterial life, whatever, in those distant objects. It'll be now, this project was just approved a few months ago by NASA. And it will go ahead. The idea is it's a 6-meter telescope. It'll roughly range from the ultraviolet to the near infrared. It won't be like Hubble, which goes like JWST, which goes to the far infrared. And it will be designed for high contrast imaging. The problem with finding planets is, if looking at planets around distant suns, the problem is the sun is a lot brighter than the planets. And if we were, say, at the nearest star and looked at the solar system and tried to figure out what's on the Earth, the problem we would have is that the sun is approximately 10 billion times brighter than the Earth, than reflection light from the Earth. So that's really challenging. I mean, I haven't done the numbers, but if imagine you've got a big searchlight you can barely look at, and there's a fly in it, and you want to study the fly. Okay, that's the issue that we have.
And
so this
to hold up like the JWST.
Nobody knows yet. This is just an idea, but it may not look anything like this. The schedule is that they've just approved it. And the next step is to look at the technology we need, because we don't have the technology yet. And then in 5-10 years from now, they will decide what the telescope is going to look like based on the technology we need and the technology we have. And then we'll launch in the early 2040s. That's the idea. So this is Carl Sagan's famous the pale blue dot. If just from 6 billion years, which is 6 billion kilometers, if you're just looking from the outer solar system around Pluto back at the Earth, this is what the Earth looks like. Okay, and that's really close. I mean, that's still in our solar system. So that's the challenge we face, but there it is. But here's one of the things that the HW, the Habitable Worlds Observatory, will do, is that we probably can't see, things like the cities or something on their planets. But one of the things in the Earth's atmosphere, we can get maybe a spectrum of the Earth's atmosphere, how the light reflects from the atmosphere of this distant planet. And if it's like the Earth, one of the things you see in this wavelength range that HW will have is that there's water in the atmosphere, and water for life on Earth is critical. Everywhere where there's water, there's life. Everywhere where there's no liquid water, there's no life. It's absolutely critical for life on Earth. Second thing is oxygen and ozone. They were created by life on Earth, right? The original Earth didn't have oxygen in it, but then microbes produced oxygen and put it into the atmosphere. And the 20% or so oxygen we have now is produced by life. So oxygen would be a signal for life, unless there's some non-life way to make it. Methane is similarly, right? Methane is CH4, is made by cows and stuff, and that's an indicator of life as well. CO2 is not an indicator of life. There's CO2 in other atmospheres. So one of the things that HMO will do is to look for these, what we call life signatures, in about 25 of the nearest solar Earth-like planets in other stars. Right now, with a 6-meter telescope, we don't see how we can even do just more than 25. So it's a very, very difficult problem. But that's the next big step. So I just want to mention something, a political thing in astronomy, how astronomy works on this kind of project. Every 10 years, the astronomers get together, form big committees, and we decide what is the important things that we need to do next. And they sign, and there's hundreds of astronomers contribute to this, discussions, debates, votes, and then we come up with a report sponsored by the National Academy of Sciences about what we should do. And it has lots of things in it, but one of the things is the signature big project, which for the 2022 report was the HWO, the Habitable Worlds Observatory. That was the big major project, but there are lots of other projects. How should we fund universities? How should we fund various things? How should we go ahead with things like the Roman telescope and so forth? This is by the National Academy of Sciences. I don't know if you know the history of it, but the National Academy was actually started in 1863 when Lincoln was president, under one of the worst years in our history, when Americans were killing each other as fast as they could. But they had the foresight to set up an organization which was to advise the government on issues of science and technology. So they voted for that. Yeah, they also had a kind of a catch to it. In the same bill, it said they would not fund this organization. So it's always been privately funded by private foundations and so on. Although the government does spend, if the National Academy has expenses, the government will reimburse it for expenses, but it won't pay it for its work. And here's the deal how this works. There have been, the first of these decadal surveys was done in 1972. At that time it was called the Whitford Committee, because Alfred Whitford, who was chair of the UCSC astronomy department, headed the committee. And they did the first of these recommendations, and they recommended that the Hubble Space Telescope should be the primary feature. And the Hubble was launched in 1992 or so, and so that worked. Then the second one was the 1982 one, which which recommended Chandra, which is an X-ray telescope, still in orbit, still working. It was a huge step ahead in X-ray astronomy. In 1991 was the Spitzer telescope, an infrared telescope, which did fundamental work on star formation and interstellar matter. It has now gone past it's no longer in operation. In 2001, the decadal survey said that the one thing we've got to do is the James Webb Space Telescope. That is what we have to focus on. And then in 2010, the Roman telescope was the focus. And then when this slide was made, this was still in progress, but they have now recommended the Habitable Worlds Observatory. But that's the big thing that we should do. And these have been hugely influential because it has given the administrators at the National Science Foundation and at NASA something to go on. You know, and I've seen, I saw one administrator hold up the decadal survey and say, this is what the astronomers recommended, and this is what we're going to do. You know, and that made that organized things. And it made us speak with a unified voice. So, and I'm told that physics has now introduced this idea and that they're going to do that as well.
Mhm.
So anyway, so the future. Yeah, so what in terms of cosmology in this course, I mean, JWST has just started, going to work on that, the Roman telescope, as well as the Vera Rubin telescope that I talked about a couple of lectures ago. Those will be big things for cosmology. But the next big step will actually be the Habitable Worlds Observatory. We're going to be looking for life in other places. However, I should mention a couple of things. The cost of all this, just you might be interested in this. If you take the NASA budget as a percentage of the total federal budget, that was very high when we had the lunar landings. It was 4%. Today, now it's reduced down to 0.5%. So 0.5 cent of every dollar you send for taxes goes to NASA. And that's all of NASA's projects. And NASA does a lot of things besides rockets. It does aeronautical research and so on, which helps the industry and so forth. The National Science Foundation budget is about 40% of this. Okay.
But is it in danger? Can Trump people erase that money?
It's interesting that you should ask this question because the answer is in this graph. This is the National Science Foundation appropriation in dollars. And you can see this year it was about $9 billion for all of National Science Foundation. And this was the there we go. And this was the projection. They have now said they are going to cut by 25%, and that'll bring it down to here. And oh no. Can you still see that?
Yeah.
Okay. And Trump himself has said he's going to cut it by half. So that means there will be no more science research in universities. There'll be certainly no TMT telescope. They have already fired 10% of the people, and Trump said he's just getting started. So they're going to end science if they can. They're going to end science as we know it. They're certainly going to end education because they're very opposed to education. I don't know how NASA is going to fare because Musk himself has Trump contracts with NASA, so they may do better for that reason. But that's the future. I think in some ways, you know, the largest accelerator in physics is in Geneva in Europe, sponsored by, although we're part of it. The largest telescope is going to be the ELT, which will start in 2028. We're not part of that. But the scientific leadership, which we took for granted for so long, that is pretty much going to come to an end. All right, let me now in order to go further, I have to get back somehow. Yeah. All right. Any questions about that? Yeah.
Yeah. Between the ELT or the 30-meter telescope that is projected for Hawaii at some time in the future and the European telescope, other than the fact that one's in the southern hemisphere and one's in the northern hemisphere, is there any functional difference between what those telescopes are designed to do?
Is there any functional difference? I don't think so. I think the original science projects for a very large telescope, which is very exciting stuff, I mean, even fundamental physics stuff, it's going to do. It's going to look at, for example, the ELT will be able to look at how very distant galaxies rotate. That will tell us how the distribution of dark matter will be, and that'll tell us more about dark matter. It'll be able to look at very, very early times in the universe very precisely. And one of the questions in the background has always been, do things like the fundamental constants, the electric charge, do they vary? Do they change in time? We don't have any evidence for that, but it would be able to check that. It will be able to check, since the Hubble constant is changing in time, right? The universe is speeding up. It would be able to measure that in 20 years. It'll be so precise, it'll actually get a laboratory measurement or space measurements of the Hubble constant, independent of these other two things, just seeing how it changes in 20 years. So it's amazing. So, but now they were all planned to do that. I think, well, I'll now put in an opinion. I think the transformational science is going to be done by the ELT, but right? I mean, it's like, we've got the Hubble Space Telescope working, and now suppose somebody came along, I mean, the James Webb Telescope working, and now somebody comes along and say, oh, okay, in 10 years from now, we'll launch one that's slightly smaller than that. Well, that will probably still do a lot of good science, but it won't be the transformational kinds of science that I suspect that the ELT is going to show us. The transformational kinds of science that JWST is doing is going to now be.
Is this science being shared? So are the Europeans, there are other countries, is the entire scientific community sharing what the JSWT is giving?
Absolutely.
And will that happen with the ELT?
Yes. I don't know the details. I mean, but I mean, the ELT has 16 countries plus Chile involved in it. And the allocation of time will go to those countries primarily. But for all American telescopes and all NASA projects and NSF projects and all European projects so far, if somebody who's not a member comes up with a really good idea, we allow that idea to go through. And other, Russia and China have been the same way. Everybody we want to have good science to do it. But the leadership, is going to be a little different. Okay, yes?
Yeah, on the Hubble telescope, you said they picked 20 to 25 planets to focus on, right?
Yeah, 20.
You said there were like 20 to 25 planets.
Yeah.
How do we determine that those are, who came up with a list of those planets? And I know that there is some studies showing that there are planets out there.
Yeah. Well, we have so far, the question is how do we know about 25 planets? So far, we found about 5,000 planets around other stars. So we now are getting a good statistical idea of what stars have planets, how many, and getting some idea of how many and so on. One of the results is that the technique, how do I put this? The technique for finding these 5,000 distant planets is such that you only have a 5% chance of seeing the planet around that star if you look at it, because it has to be oriented in just the right way to see it. Okay, and so they look, and 5% of the stars they look at have a planet. So that means practically all the stars they're looking at must have planets. So that we know now. And that's something new. We didn't know that 20 years ago. So all of them have planets. Now we're also getting the distribution of planets, big planets, little planets, stuff like that. That's still a little bit worrisome because we're seeing more and more planets as you get from big giant Jupiter, even bigger than Jupiter, down to smaller ones the size of Neptune. And there's always more. But then you get to Neptune and it seems to level off. And it doesn't, it seems to be not some more. There may still be some technical difficulties, but it seems to be real. Earth-like planets are difficult for us to see with this technology, and we have just a few. Typically, they're super Earths, 2 or 3 times the big as the size of the Earth. And anyway, from all those numbers, we can now estimate, and we can also know how bright a planet at a certain distance is going to be. And of course, the further away it is, the fainter it is, and also the further away it is, the smaller the distance from its star gets, so the harder it gets. And so from all that, we can estimate what this telescope might be able to do, a 6-meter telescope. And it's not, it's somewhat worrisome. It's only 25 planets that they're thinking of right now. But by the time the technology develops 10 years from now, that number may change. I guess either way, but it might get better. But so 25 Earth-like planets, but there's probably a lot more super Earths that are twice the size of Earth and stuff like that. So I think it'd be a really interesting project. And also, incidentally, it will have some applications that are non-planetary. It's a 2.4. It's a Hubble-sized telescope. It's going to do a lot of stuff. Okay, any question? All right, where are we now? Okay, well, let me now finish off here. This is this is the James Webb Space Telescope picture that I was talking about. So what are some of the questions? So one of the things we'd like to know now is how, for this century, how did the first stars and galaxies form? What is the dark matter? I'd like to understand that. What is the dark energy? Is there life in the universe other than our own? If there is, what is it like? How does life begin on planets? That may be more a question for biology, but those are some of the pressing questions that we have right now. For maybe in the future, we might ask, what is space like at the smallest and largest scales? Can we get a unified theory of gravity and quantum mechanics? We don't have that right now. Are there other universes besides our own? How will the universe end? How and why did it all begin? But who knows if we'll ever know the answers. So those may be much more distant questions. So I'm going to end by just saying, this is a picture my daughter took, actually. So, but I want to, it's been said before, and I'll just repeat again. I mean, certainly the idea of understanding the universe, understanding time, distance, history of the universe, that is part of our understanding ourselves and our understanding our place and the meaning of our lives. So I will end with that. Okay. Great.
Thank you. Excellent.
That's great, Roger. Take care.